All right. Good morning, everyone. For those who are going to be reviewing this via the recording, thank you for taking the time to listen to this presentation. This is the preliminary design review for the BX-4 payload as part of the Aero 495 project, working with Professor Kamba. Um, just sort of the table of contents that we are going to be going over. A lot of you are familiar with our payload now at this point from our previous presentation, so today we want to touch on some more of the technical aspects of our design and present our finalized design. So in doing that, we'll go over the mission overview again. We'll talk about the full payload summary, go into the subsystem summaries, and then finally give a full systems overview. So our mission statement hasn't changed. We still want to demonstrate the ability of U of M engineering students to precisely design, build, and deploy complex aerospace systems. Our goal here is to deploy a 2U-sized payload from a rocket above the Kármán line, control and orient the payload to acquire multi-angular images and video to provide visual evidence of launch vehicle mission success. So with that, the first thing we need to identify is what our launch vehicle is. So our launch vehicle that we'll be going up to 100 kilometers on is the Tangerine Space Machine. It's a rocket designed by NASA, which is a on-campus student org. It's going to be a single-stage liquid-propelled rocket, and it's part of the Base 11 challenge, which is a goal to design, a rocket of these specifications to reach 100 kilometers. Some of the difficulties that we're going to have with our integration there is that the rocket has no reactive spin stability, so we are not going to have any gauge on how much we're going to be rotating beforehand, and we won't be able to ensure that we won't have any rotation rates upon deployment. Along with that, we have minimal ability to communicate with TSM while we're sitting in the rocket. We will define it a bit better later, but you can see on the right here, we are going to be in this area between the avionics bay and the helium tank. As I mentioned, it will be a lot clearer further in the slides. So our mission objectives, we want to capture video throughout the duration of the mission. We want to precisely deploy from TSM via a rocket deployment signal. We want to stabilize and orient the payload to face the rocket. And then we want to be able to recover all the flight data. Some of the secondary and tertiary objectives involve taking precise images during this mission and being able to orient ourselves from looking at the rocket to looking at the Ann Arbor horizon, and then taking in all of the flight data that we're getting and being able to verify the true flight trajectory. And as you'll see in a little bit, how it sort of matches up with our pre-flight simulations. So just, here are our level 1 mission requirements. They have slightly changed, but haven't really changed since last presentation. Some of the things to highlight is this reference column on the right side. What you can see from that is we had to develop a lot of our own internal objectives, and that raised its own issues in that we had to really push the limits on what we thought we were capable of doing, opposed to getting a set of requirements and seeing if we were capable of meeting them. So then those requirements flow into our level 2 requirements. Again, these are very similar, and we just have, again, the reference to be able to flow down and see how these requirements decompose the L1 requirements, and we'll be able to see the same when we get to the subsystem requirements. Here's just a basic traceability matrix of the requirements, and again, just that same idea that we can see how, achieving requirements works all the way up to our ultimate mission goal. Here's our project timeline. Again, today is the preliminary design review. We have quite a bit of a ways to go. We do have quite a bit of time, however. The goal of this class is to be ready to give a formal critical design review by the end of the semester. So we want to be giving that presentation on April 21st. From there, that will allow us time over the beginning of the summer to do all of the system level testing and all of the full flight simulations to make sure that this payload is fully ready to go. With that, we want to be done with the flight payload design by the middle of June. However, we do have quite a bit of margin there if we do need to flow over because we'll have a handful of students who will be available at some capacity over the summer to work on this payload. With that, I'm going to turn it over to Juliet for the payload summary.
Hi, so this is just an overview of our concept of operations, the same as the last time we had a meeting. So our basic concepts is that we will lift off inside the TSM, and then we will eject from the TSM and stabilize, rotate around to image the TSM, and then after that we will be taking image of the local horizon. Then we will deploy a parachute and land and be recovered by the staff at White Sands. This is simply a breakdown of our ConOps by subteams. So the image on the right is basically showing when each subteam is active and when they are going to be in action. So as you can see, CDH EPS will be on the entire time. The cameras will be on the majority of the time, and then other subteams will have little bursts of activity throughout the duration of the mission. This is a definition of our coordinate systems that we will be using for the rest of this presentation. So we have two coordinate systems, one for the rocket, which is centered on the body of the rocket, and one for the payload that is shown in green, which is centered at the payload center of mass. So we created some trajectories of the parachute, or sorry, the payload and the TSM after deployment. The point of these trajectory scripts was to determine how far away from the TSM the payload would land after being ejected. And what we saw was that no matter what spin rates or ejection velocities we put into the script, the payload was not landing very significantly far away from the TSM. This is significant because we will no longer need to have a GPS in order to be collected by the personnel at White Sands. So this is very important because in our last meeting, we needed a GPS, and now we have been able to eliminate that hardware and that necessity. Some things about the payload environment. On the thermal environment, we will be between 200 and 350 degrees Fahrenheit for 15.5 to 41.5 seconds. We'll have internal rocket pressure that will be equalized with external pressure. And we also have a vibration profile that we gathered from NASA on the TSM. So this is just a big change that we've had since the last meeting. Our payload has increased significantly in size. We've been able to work with NASA to get that to work out. So now our current payload size is 8 inches in the Z direction, 6 inches in the Y direction, and then 3 inches high. And we are located right underneath the avionics bay. So this is a real fast rendering of what the payload is going to look like and where it is going to be in the TSM. So on the left-hand side, you can see the payload is integrated in the TSM. The outside shell of the TSM is the TSM body is not shown on the bottom half, just so that you can visualize the helium tank and the payload itself. Will be interfaced directly to the TSM using guide rails, and then as you can see on the right-hand side, this is a basic layout of the components inside of our payload. So we have the reaction wheel assembly on the bottom left, the imaging cameras on each side of the payload, and then the parachute taking up the bottom right side of the payload. And then this is just a video to show, to better show the locations of everything within the TSM payload. So This is basically a slide explaining how we are making sure that we are keeping on track with our mass margins per each subteam. The way that we are basically color coding this is whenever you see a mass budget, if we are within our mass margins, we will label it as green. If we are, just on the edge, we'll label it as yellow. And if we're outside of our mass margins, it will be labeled as red. As you can see from this slide, per subsystem, we seem to be outside of our mass margin. But if you look at the bottom table, you can see that we are still within our total mass, allotted mass. It's just per subsystem, there are a little bit of differences. So we are currently working on that to lower the mass for each subsystem. But as you can see, we still have not exceeded our total allowed mass. This is an overview of the power allocation. So on the top, you can see basically the entire power used at any given point within the mission. And then on the bottom, you can see it broken down by subsystem. So you can see that ADCS is taking up a large amount in the middle portion, and CDH will be taking up a minimal amount of power throughout the entire mission, and so on. And now we'll go into subsystem summaries, and I will hand it off to Owen.
Thanks, Juliet. So I'm going to be leading you through the imaging and video subsystem. And so this is the team that's responsible for capturing and storing all the image and video data. And so we'll talk about our requirements in a second, but our overall design is that we have 2 video cameras, which run at 4K 60 FPS. You can see they're kind of opposite opposed there, which gives us a really good field of view. And then we have 1 imaging camera, which is an 8 megapixel kind of normal FOV type camera. And this connects directly to the flight computer and has a couple different jobs. So here's our requirements. I won't go through all of them, but it basically just defines how long we need to take images and video and kind of what the quality standards are for those as metrics of success. And it also talks about how we need to be sure that we're storing the data and able to recover it after landing. So here are the selections that we made. So as I said, we had requirements which kind of flowed down. Then we did a trade study for each of these to figure out what the best component is. We ended up with this 10.3 gram camera, which is really, really small, not a lot of mass, but it does give us 4K 60 FPS, which is really what we wanted to get really good quality video. This also stores all the data directly on an SD card. We're going to have 3 SD cards on the payload, which will give us a little bit of redundancy should something happen to one of them. And then for our imaging camera, we're using the RPi camera V2 because this integrates really, really well with our flight computer, which is RPi. And it also only weighs 3.4 grams, but has an 8 megapixel sensor. And so these are our kind of component level choices for the imaging team. Here you can kind of see a little bit of a wiring diagram. Basically, the imaging camera is wired with both power and data to the RPi. And then the video cameras will be provided power through our power bus, but get signals from the RPi to start and stop. And these video cameras start recording as soon as they turn on. So the RPi is just going to send a signal to the power bus, which then enables the power switch basically. And then the video cameras will start recording. And once they're turned off, all the data is stored on their respective SD cards. Here's our plans for verification testing. So we did our power draw test back in February, and now we're kind of kicking into our more rigorous testing. So we're working on the vacuum test first, which we've made some progress on already. We've set up the experiment, but we haven't actually run our equipment through it yet. So we'll be doing that over the next week. And then we're going to be doing some thermal testing as well. A couple of different system level tests will take place later in April and also into May. But this is, kind of the plan of how we're going to get everything done so that our components are ready to go. This is our mass and power budget. So you'll kind of see they're color coded based on the level of certainty we have. But as I said, all these cameras are super low mass. It's about 50 grams even with our wiring margin in there. So we're really happy with that. For power, it's going to take about 6 watts when we're running everything at the same time. And so that's right about where we want to be. But yeah, we're really happy with the mass, and it hopefully will leave some room for the other sub teams. All right, I'm going to pass it off to Liam, who's going to go through the ADCS.
Thanks, Owen. Hey, everybody. My name is Liam Spence. I'm the BX-4 ADCS sub-team lead. I'll be presenting our slides on the Attitude Determination and Control System subteam. So ADCS is responsible for implementing solutions that allow our payload to autonomously determine and control its attitude during the mission. We will achieve this through the use of an integrated sensor array, various control algorithms, as well as attitude control hardware that will be dynamic during the mission. So like IMG, I won't go very in depth with these requirements, but imaged here and in the next slide are an overview of the requirements that ADCS has been using to drive our subsystem design. They cover the functional, operational, and constraint requirements that we have had to follow, and they are all derived from upper level requirements that we received from either our stakeholder or the overall mission design. So to kind of break things down, ADCS is comprised of three main components, each of which will be elaborated on in the following slides. These include attitude determination sensors, like I mentioned before, dynamic attitude control hardware, and the imaging processing and inertial control software that ties both of our hardware aspects together. Going a bit more in depth on attitude determination, our payload will achieve autonomous attitude determination capabilities using a 10 degree of freedom sensor, as well as the still imaging camera from the IMG camera array. The 10DOF sensor we chose measures the dynamics and orientation of the payload using an integrated gyroscope, accelerometer, and magnetometer, all integrated into one low mass board. This board also includes an altimeter that will be used by the reentry and recovery subteam in the later stages of the mission, and they'll go over that a bit more later in this presentation. The still imaging camera that will take pictures of the payload surroundings that IMG has now integrated. These images will be used for, will actually be processed using an onboard processing script that will be explained a bit later in these slides in order to identify and track TSM in real time. This slide covers the technical capabilities of our 10DOF sensor. So functionally, the sensor measures the rotation rates, accelerations, magnetic orientation, and altitude of the payload. And each of these measurements are, the areas of each of these measurements have large enough ranges and also fine enough sensitivities to adequately measure the expected values that we will see during the payload's operation and flight. Here you can see a bit more of our attitude control hardware. We will achieve our attitude control using a 3-axis reaction wheel assembly. This will be comprised of one reaction wheel, which is a combination of motor and a flywheel, mounted parallel to each of the 3 primary payload axes. The reaction wheels will be powered by electronic speed controllers, or ESCs, in order to apply a torque to the specified flywheel to spin them up to a high RPM. The spinning flywheel will then impart angular momentum into the payload such that it counters the momentum imparted to the payload during deployment and the previous flight during ascent. Payload angular momentums from both the deployment and the flywheels that are of equal magnitude but in the opposite directions of one another will lead to a net zero rotation rate in that axis. And so spinning the flywheels faster or slower than this rate that's required to negate the payload's own angular momentum allows our ADCS subsystem to properly control its attitude in all 3 axes during the mission. The 3 main components of our reaction wheel assembly include brushless DC motors, electronic speed controllers, and metal flywheels. For our motor choice, we selected a high-performance motor model commonly used in acrobatic and racing quadcopters due to its high torque and max RPM ratings. The ESCs we selected host an onboard microcontroller that allow for each of them to be individually programmed and tuned outside of any integration with the payload's own flight computer. This will allow the ESCs to have different fail-safing modes in response to a variety of off-nominal power conditions that we might experience during flight. And they also run their own closed-loop PID control using feedback from the 3-phase motors to properly spin up the flywheels as commanded. For our flywheel design, we currently have selected discs made of brass. Due to the simplicity of manufacturing and the high material density that these provide. We anticipate continuing to use brass as our material for flywheels. However, we are currently pursuing other more complex flywheel geometries that will allow us to make the reaction wheel assembly overall more compact, as well as increasing the moment of inertia efficiency of each flywheel in each axis. So in addition to the flywheel considerations, some of the future work that we have to do will be collaborating with the integration and deployment team to determine the feasibility of adding additional sensors into our payload. These sensors are going to be sensing rotation on the motor if we end up going with them, and will allow us to have more fine-tuned control of the motors spinning at lower RPM. This will in turn allow the payload to have very, very precise control in its rotation rates in each axis, as compared to our current design. So while centralist control, or the current design we selected, is feasible and achievable with our current hardware selection, exploring a more sensored control using the external motor encoders would further increase our control capabilities of the payload. I'll now talk a bit about the software components of the ADCS subsystem. So our final flight software script will be broken up into 4 main scripts that will run sequentially upon payload deployment from TSM. You can see each of these phases in the rows of the table on the screen. Initially, ADCS subsystem will attempt to negate the rotation rates imparted during deployment in each payload axis, as I previously described. Now, once these are all approximately 0, the next script will then begin the process of finding and tracking TSM using the images from the IMG script. This script in particular will be further elaborated on in later slides. Once TSM has been imaged for a while, the payload will then reorient itself to point the imaging camera in the direction of Ann Arbor, or more specifically the horizon in the direction of Ann Arbor. And when completed, the payload will then attempt to reorient itself such that the parachute is pointed vertically away from Earth to aid in the reentry process. So our current progress, we have created the pseudocode and logic flow for each of these software scripts, as well as nearly completed a Simulink program that will help us refine the PID gains that will be used in our overall flight control loop. So each one of the scripts presented in the previous slide will implement closed loop PID control using the TENDOF sensor data as its feedback. The output of these scripts will then be commands to the reaction wheel assembly, which will be processed and implemented as torque to the motors by the ESCs that I described earlier. In the near future, we will determine additional appropriate time-based cutoffs for each of the scripts' end condition to ensure that our payload will not become latched up in one of the intermediate scripts during the actual mission. So now I'll hand it off to Trina to go over a bit more of the image processing aspects of the ADCS software.
Hi, my name is Trina Dada, and I will be talking a little bit about the ADCS image processing script. So we'll be using OpenCV, an open source image processing library, to identify and track TSM given images from the still imaging camera. The script will use a combination of edge detection as well as color distributions to identify the contours of Earth, TSM, and space. Once TSM is identified in an image, we will calculate the location of the center of the contour and orient our spacecraft to match TSM's center with the center of our still imaging camera's field of view. As it currently stands, the script reads in an image, performs a Gaussian blur to smooth out noise, and uses canny edge detection on the blurred image to find the important edges. The result of this process can be seen in the leftmost image. Our next steps include identifying the actual elements. For example, TSM should have 2 long parallel edges, and creating histograms of the RGB values within each contour to verify we've correctly identified the elements. For example, we can expect nearly all zeros for space, pretty even RGB distribution for TSM, and a higher blue content for Earth. From there, we can calculate the X and Y shifts required to match TSM's center with the center of our still imaging camera's field of view and back out the rotation required in each axis. Now I'll hand it back to Liam to talk a little bit about our system interfaces.
Yeah, thanks, Gina. So if it is not yet apparent, ADCS is a highly integrated subsystem, and we interact with many of the other subsystems actually involved in the mission, as you can see in this overview image here. Our attitude determination uses its own TENDOF sensor as well as IMG's imaging camera, and then data from both of these sensors will be collected for attitude determination. This data includes the payload dynamics, as I mentioned earlier, as well as image data that is sent back to the payload's flight computer, as Trina just described. The payload's flight computer then uses the onboard script to both process the imaging data as well as the attitude determination data. This is one of the primary components of our command and data handling subteam, and they will go over a bit more about this later in the presentation. All of ADCS's electrical components will be powered off of the payload's power bus, as you saw on that previous slide. And it'll also be further described by the electrical power systems subteam. So the commands that will be output from the flight computer that you saw in the previous slide are then going to be delivered to the ESCs, where they will be processed by the onboard microcontrollers and used to time the power delivery from the overall payload power bus to each of the motor's 3 phases. These motors will then spin up the flywheels, and the flywheels will spin in the many thousands of RPM during the mission, which requires us to have heavy collaboration with the structures subteam in order to design adequate mounting solutions so that everything maintains structural rigidity during the flight. So outlined here is the current status of our subteam's testing. Thus far, we've completed the testing required for our ADCS hardware selection, and we've begun processing example images of other suborbital rocket flights using our image processing script that we saw earlier. We are planning further system-wide testing for both our hardware and software components to further characterize the performance and reliability of the ADCS subsystem as a whole. Finally, you can see here our subsystem's current mass and power budget. Our design we presented throughout these slides currently falls under the specified mass limit allotted for a subteam by systems, and we will soon be completing further tests using our attitude control hardware to refine our estimated power consumption. Thank you all for listening to our subteam's portion of this presentation. I'll now pass it off to Alec to go over the CDH and EPS subsystem.
Thanks, Liam. My name is Alec Ash. I'm the lead for the Command and Data Handling and Electronics and Power Systems subteam. Our subsystem is responsible for managing all of the data and power distribution of the payload system. We are going to be placing a Raspberry Pi 4B model on the inside of the payload and use lithium polymer batteries to power the entire payload. Our subsystem interfaces with every other subsystem inside the payload, as well as the TSM rocket itself. Here's a list of our requirements, just to highlight some of the changes since our last presentation. We will be implementing the control scheme as designed by the ADCS subteam, and we will be receiving a deployment signal from the TSM, which we will then pass on to the deployment mechanism. For our subsystem design, we started with our choice of microcontroller. We chose to go with a Raspberry Pi 4B, as it has up to 8 gigs of RAM and has a 1.5 gigahertz CPU clock. It is the most cost-efficient microcontroller, as it costs only about $75 and is more than capable for all of our purposes. This microcontroller can easily interface with all the necessary subsystems, as it's capable of transferring simple input-output data, as well as more complicated serial, I2C, and PWM interfaces. For our battery selection, we chose lithium polymer over the alternative, which was lithium ion, due to its high instantaneous current capacity, as well as its much greater safety. Lithium polymers do have a lower power to mass ratio, but we decided that the pros much outweighed the cons. The voltage from our power supply will have to be stepped down to 5 volts for the Raspberry Pi, but our motors will be able to receive the full 4S voltage configuration. And the Raspberry Pi has built-in 3.3 volt rails, which will further step down the voltage to the 10 degree of freedom sensor, as well as other components. For our design of the connection to the rocket, we chose to go with an optical-based connection, loosely based on the design of an optocoupler, which is the schematic you can see on the right. The basic mechanism is that a light turns on, which closes a phototransistor switch, which is placed next to it, which then relays the signal to our flight computer. We chose this configuration because it mitigates the need for large voltage regulation. The signal coming from the rocket itself will be at about 12 volts, and this is far too great for the flight computer to handle. So if we can take that 12-volt signal and convert that to a 3.3-volt signal without active voltage regulation, this simplifies our design greatly. This also reduces the risk of the mechanism being damaged or completely broken by vibrations or small movements in components during launch and ascension, as if we went with a magnetic or spring-loaded connection. A closer look at our deployment circuit, you can see that red box in the top left represents the voltage that's coming from the rocket. That's going to come in across that top horizontal line, be relayed by our optical connection, and be read into the Raspberry Pi as our deployment signal. Once you receive that deployment signal, we will then send a signal to a MOSFET switch, which will close that circuit on the left, redirecting the voltage from the rocket to our deployment mechanism, initiating our deployment. And since we have no physical connection over the optical connection, the payload will be able to eject swiftly and easily. To go a little bit more into our interfaces with the other subsystems, we are going to use a PCB to distribute the power independently of the RPi, and this power bus will include all necessary voltage converters. We are going to mainly use GPIO pins to send both binary input-output signals and the more complicated information to the other components. The Raspberry Pi imaging camera that Owen mentioned earlier will be connected through the camera port. The video camera will transmit data over the serial interface pins, and the IMU sensors will be able to transmit data over the I2C pins. And then again, this is just another look at the overall deployment mechanism. We will receive launch and deployment signals from the rocket, and we will relay that deployment signal to our deployment mechanism, which will close the switch on that power, redirecting that voltage from the rocket to our deployment mechanism. A closer look at some of the data that we will both receive and transmit to the other subsystems. To the IMG subsystem, we will continuously power the video camera, as well as send a trigger signal to take still images. The flight computer will implement their computer vision algorithm to detect the edge of the rocket as a reference for our attitude determination. For the ADCS subsystem, we will read in and log their telemetry data, which will be used to reconstruct the true flight trajectory, as well as feed this data to the control script, which will then be converted to commands sent to the ESCs. For the reentry and recovery subsystem, we will send a signal to deploy their parachute upon reentry. And finally, we will receive signals from the TSM rocket through our phototransistor at the launch and deployment events. Here's just a quick look at our verification testing. We've just about completed our testing on the optical connection, and I've completed the testing on our sleep state for the RPi on the launch pad. The next step will be to conduct thermal and vacuum chamber testing to ensure that the RPi can operate at all of our expected conditions. We will then test the data transfer from the IMU sensor through the flight computer to the ESCs, as well as verifying our triggering of the camera, deployment mechanism, and parachute. And finally, we will end up testing our full script, as well as our full battery output. And finally, this is just a look at our subsystem mass and power budget. We come in at a total mass of 289 grams roughly, which is under the allotted 300, as well as a total power of 16.8 watts. And I will now pass it off to the structures subteam.
Thank you, Alec. My name is Rodrigo. I'm the structures lead, so now I'll be giving you an overview of our subsystem. So structures is responsible for housing and protecting the payload components throughout all stages of the mission. The way we will do this is by a 3D printed shell, also with a 3D printed lid that will bolt on top. And this shell will interface with the outer rocket skin, the deployment mechanism, and the parachute housing. So here are requirements. I'll highlight that obviously the structure shall house all components through launch, deployment, and reentry. We shall not jeopardize the structural integrity of our launch vehicle, the TSM, and our structure will fit within the allotted payload bay in the TSM. So our subsystem design, as you can see in the top left picture, we will have a front plate that will mate to a larger flange that connects to the outer skin of the rocket. This component will not be 3D printed. It will be made out of the same aluminum alloy that the rocket is made out of, just for ease of interface. We'll have 4 rails that will maintain the shell in position throughout launch, and a cylindrical cap at the back that will allow for a smoother CO2 deployment connection. You can see from the picture to the bottom right, that mesh, the parachute housing will be directly printed into the shell. This helps us from a mechanical complexity standpoint and also reduces the amount of mounts and brackets needed on the payload. Sorry, it lagged for a bit. Our subsystem interfaces. The cameras will have 3D printed mounts and have a glass protective lens on the payload shell. Reason for this is, you can see in the top left picture, the camera facing the curved edge. That curved edge is going to get very hot due to aerodynamic heating. So a protective lens is needed to make sure the cameras do not sustain any sort of temperature damage. The RPI will be suspended on standoffs, which will be directly printed into the payload with the 10-degree of freedom sensor directly attached to that board. The reaction wheel assembly, which is that silver box you see in the top left, will be in its own isolated mechanism, which will then bolt into the payload. So to validate our design, we decided to run a structural FEA on the payload design. The purple regions that you see are fixed supports, meaning it cannot move in any of the 3 directions. And then we applied an acceleration to the entire body. The acceleration applied was 67.2 meters per second. This was a worst case scenario number that we pulled from the flight simulations that NASA did on their vehicle. And so from this, we see a max stress of about 2 megapascals at the interface between the rail and the shell lid. I want to emphasize that this is a strictly mechanical loading. This is not coupled with the thermal loading we expect to see. That simulation is still being refined. It's not pictured here, but the stresses inside the shell itself are minimal. So this is good. It'll have very little impact on the internal components. And so taking this max stress and the data from the manufacturing company that will 3D print this shell, we get the following safety factors in the 1, 2, 3 direction. So the 1 direction being the strongest, around 40, the 3 direction being the weakest, around 19. So here's our mass and power budget. As structures, we don't really have a power budget. The shell body and the shell lid mass estimates come directly from the SolidWorks file. We are assuming about 25 grams for the bolts and mounting, although that hasn't been measured yet, with an estimated margin of around 80, which brings us to a total of 584, which is still below our allotted mass of 600 grams. Now I'll hand it off to integration and deployment. Thank you.
Hi, my name is Rachel Byram. I'll be presenting for integration and deployment. I'm also the lead for the sub-team. So our sub-team is in charge of creating a deployment mechanism for the payload to deploy. And we're also responsible for integrating with the rocket. So we've done this by creating a CO2s, CO2 ejection system, creating guide rails and plates for support, and then mounting in between the avionics tank and the helium tank and the avionics bay. These are our requirements. One of the things that I want to point out is that we will deploy at between 1 to 2.5 meters per second. That's the desired speed that we're going for. So for the payload supports and integrating with the rocket, we're going to have guide rails that are highlighted in red. They're basically L brackets on all 4 corners of the payload. And then we also have a bottom plate and a top plate to mount those into. It's the bottom of the avionics bay and then on top of the helium tank. And this limits the direction of motion for the payload so that it can only deploy in the plus Y rocket direction. The rails also have a low coefficient of friction and low coefficient for thermal expansion. The other supports that we needed were like pipe brackets to put on the CO2 deployment system that will mount into the top and bottom plates. We put 3 of these. Our biggest concern was if it's going to match our vibrational profile and the vibrations that we're going to see. So we did a quick vibration analysis and found that the lowest mode is at 2769 hertz. And that is in the Y direction, in the direction that we'll be deploying. And then the second lowest mode is at 3850 hertz, and that is in the rotational direction. And you can see some videos here of the analysis that we did. To keep the payload in place on ascension and before we deploy, we have nylon fasteners that are mounted into the avionics plate and the Teflon coated rail and into the payload. And then when the CO2 pushes against the payload and has that ejection force, the pins will physically shear off so that the payload can deploy when we want it to. The required shear force per fastener is 39.7 pound force. And this is a breakdown of the CO2 deployer that we're going to be using. We're going to be using 8 grams of CO2. We're going to have to partially vent that because it provides a little bit more force than we want for our desired range of velocity. So we're going to have to vent that, but we are using the smallest available, which is 8 grams of CO2. We really wanted to have a part that was manufactured outside of ourselves, and so that it's been reliably used in other aerospace applications. It's triggered using the MJG firewire electric match and ignites the black powder, which pushes the CO2 bottle and opens the pin, allowing the payload to deploy. And then for our safety, because we're using black powder and everything, we are going to be using remove before flight key tags, which disengages the electrical match connected to the black powder and the CO2, just for team safety leading up to launch. And this is our verification testing that we're doing. Right now, we're in the middle of testing our CO2 output force and verifying our feasibility for our system. And then once we do that, then we'll move into thermal testing and verification testing for the rest of our system. And this is our mass budget. We come to a total of 428.2 grams currently, which is under our allotted 450 grams. Okay, and then I will pass this off to Jacoby for R&R.
Thanks, Rachel. Yes, my name is Jacoby Crochelle. I am the lead for the reentry and recovery subteam. So kind of a subteam overview. We're going to be using an altimeter-driven parachute deployment using line cutters. So on the right side, you can see kind of the closed configurations with the netting or webbing retaining the parachute. And then underneath, you can see after those lines will be cut and how the webbing will fold off to the sides, allowing the parachute to exit the cavity. This is shown as an exterior housing just for clarity, but it will be directly integrated into the shell as will be shown later. And the main responsibility is decelerating the payload to ensure that all data remains intact. So here are our requirements. They are similar from the last presentation. The one to note is the parachute shall decelerate the payload to 5 meters per second or below for landing. This will provide sufficient deceleration in order to recover all data intact. Here we have the impulse and velocity of the reentry stage. So the time scale begins at 80 kilometers. We're going to feel about 5.7 Gs of acceleration when the parachute deploys, and then about 22 Gs when it touches down. on the right side, you can see the velocities with a peak velocity of about 1,200 meters per second and a parachute impact velocity of about 4.72 meters per second. So for subsystem design, some of our selected components were the Iris Ultra 36-inch parachute. This was selected because the parachute parameters allowed for a velocity sufficient to be within that 5 meter per second impact speed. And the parachute system will be comprised of a swivel shot cord as well as the parachute. We're going to be using the Tinder Rocketry Piranha line cutter. This will shear the webbing and allow the parachute to release when triggered, and it's going to be powered by an electric match. And then we'll be using the Altimu 10 degree of freedom data from ADCS in order to know when the E-match should ignite. So for the netting material, we plan on using solid braided nylon rope. This should be sufficient in holding it in with a tensile strength of 320 pounds of force. The barrel swivel will be used to reduce risk of entanglement once the parachute is deployed. The shock cord is used to dampen the impact after parachute deployment, and the MGJ firewire will ignite the black powder that severs the netting. So here's kind of our interface with the flight computer. We'll be receiving signal in from the Altimu 10 degree freedom sensor. That signal will be processed by the RPi and provide signal to the power bus in order to ignite the E-matches and therefore the line cutters. And so the process for that is the 10 degree of freedom reads into the flight computer, and if all conditions are met, it will allow the signal to the power bus that will ignite the E-matches and the line cutters. So here you see our interface with structures as a direct integration. On the left side, you can see where we're at, and on the right side, the highlighted bottom cavity of where the parachute will be sitting. Also note that there's an eye bolt in there, which is how we plan to mount the parachute to the shell, and it will be screwed into the lid that is not pictured here. As for testing, we plan on getting started in the next couple of weeks with parachute packing tests and line cutter tests, followed by shell integration, altimeter data stream test, wind tunnel deployments test, and then finally component survivability tests. Our estimated mass right now is about 189 grams, which is under the 200 gram mass limit, and the estimated power is about 11 watts. And now I'll pass it to Joe to talk about the manufacturing plan.
Hi, I'm Joe Carey, and over the past couple of months, I've been heading up the manufacturing plans as we move forward with finalizing our design and move towards actually manufacturing parts of our payload. There's a combination of parts that we're making, buying, and reusing in our payload. And for this presentation, we'll focus on those that we are actually making. So on the slide, you can see the front flange, which will be water jet to the correct size, and then rolled and eventually drill pressed for needed holes. There will be the shell, which will be 3D printed, and then there will be the flywheels for the ADCS control system, which will be cut with both a lathe and then pressed with a drill press. On this slide, you can see more about the reaction wheel assembly, which will be a combination of buying stock components from McMaster and then cutting them down to the proper size and drill press using a drill press to make sure that they can integrate correctly with the rest of the payload. Very similarly to that, for the deployment rails, we will buy standard L brackets from McMaster and then cut them and drill them down to the correct size in order to integrate with the rest of the payload. And again, same thing goes for the camera support brackets for both the video and still cameras. We will buy standard parts from McMaster and then use the bandsaw and drill press to integrate them with the rest of the subsystem. To be able to manufacture these parts, we have a couple of different places on campus available to us, starting with the mechanical engineering machine shop, which has a bandsaw, drill press, a mill, a lathe, a water jet, and an arbor press. There's then the Wilson Center used for team projects, which has all the same capabilities as the mechanical engineering machine shop, with 3D printing capability, sheet metal rolling capability, and a few more advanced milling stations as well. And then there's the DuderSat makerspace if we need additional space for 3D printing for the parts of the project. And now, yep.
Yeah, I can take over from here for risk management. Yeah, with all that manufacturing guide stuff, it's just going to make the payload build a lot quicker, and we'll touch more on that as we finish up the presentation with the project timeline. First, we just want to talk a little bit about risk management. The way we are sort of identifying risks is by looking at a couple different off-nominal ConOps conditions. So some of the ones that I just want to highlight is in the case that a camera fails, in the cases that we have a slow start from ADCS, they're not able to detumble us. In the case that we're not able to deploy in the right orientation, just trying to cover all the bases for what would still happen within a flight and not be a scratched flight. So some of the ways that we're ranking our risks, you can see the provided tables here. We're not really focused on cost risks right now. We're more focused on things that are going to impact our scheduling and our technical impact. So the scoring for those is shown below, but it's just really important to note that for the technical impact, it's just about the scale, whether it's going to impact a single component of a subsystem or all the way up to the entire BX-4 payload. So here we can highlight a handful of risks. Some of the biggest ones, as I mentioned, would be if we have blurred images from the camera, what that's going to do is prevent us from being able to use that computer vision software that we had mentioned earlier. So that's really going to affect our ability to ensure that we're looking at the TSM and then sequentially look at the Ann Arbor horizon. We gave this a likelihood of 3 and an impact of 3 because while we'll still be able to video the entire flight, we won't be able to show we have the ability to orient our payload. The mitigation strategy here is we're going to be testing the camera response under vibration and looking for some autofocus capabilities to reduce any sort of issues that we might have trying to take images. For component overheating, there's the concern that without air conduction from the air, the RPIs and the cameras and other electrical components will overheat quicker. Again, this is going to have a pretty heavy impact because if our RPI is no longer working, we won't be able to communicate with anything on our payload. So we gave this an impact of 4, but we do think that based on our testing strategies that the likelihood is going to be very low. We're going to be vacuum testing all the electrical components we have. And if we see that they are having issues with overheating, then we're going to use an aluminum mounted heatsink. Then for parachute testing, we have had difficulty finding testing availability within the wind tunnel. This is just going to set back our ability to ensure and validate the deployment orientation and making sure that the packing is sufficient. The worst case is that we will have to sort of simulate this on our own, trying to use possibly a car and using that as to get us up to speed to try to replicate our deployment. Then the last one that I want to highlight is the SD card recovery. We really need to do heavy testing on this to have a very strong characterization. There are impact force regulations, sorry, not regulations, specifications for the SD card. However, we want to make sure we fully know those and can understand what levels of impact will effectively break or not break the SD card. There's some other risks here. I don't think it's worth our time to go into them too much detail, but it has to do with the reaction wheel failure, our deployment failure, some sensor issues, and some phototransistor issues. We can see the resulting risk chart here, and that we have a lot of medium risks and not too many high risks. However, we are going to be trying to mitigate all of these risks. There is none, with the exception of risk E, there's none that we're just going to be watching for now, because we feel that with the testing plans we have discussed within this presentation, that we will be able to mitigate all these risks naturally. Then the last thing we want to talk about is our system verification and validation. This is just a quick showing what we want to do once we have the system fully ready. We want to be doing a full payload vibration test using that vibration profile that was provided in the environmental analysis slide. We will have to coordinate, but we should have access to the Space Physics Research Lab vibration table. We have worked with Dr. Van Noord using that table for previous payloads, so we are very comfortable that it will be able to accomplish what we need it to. The next big test we want to do is thermal vacuum testing. We want to hopefully test the entire payload, simulating that temperature profile we mentioned previously while running some of our subsystems to really get an idea of how hot all the subsystem components are going to get. We aren't exactly sure on the total feasibility of this, but the backup plan will be similar testing, but just within subsystems themselves. And then the last thing is we want to test the payload shell impact, the ability for the payload shell to survive impact. We will be able to simulate the impact velocity and possibly some higher speeds, so we have a level of confidence in our payload shell being able to survive the touchdown. Here we just, last thing, we want to look at the timeline again and note that the next 2 months of this project, while only one of them is within school, the other will run into the summer. As I mentioned previously, we have some students, including myself, that will be here over the summer and able to commit time to this project. So the focus from here is all testing and all ensuring that our design is going to meet our requirements and is going to meet our mission objectives, and provide, undeniable evidence that we are capable of achieving this goal of deploying from a rocket, orienting ourselves toward the rocket, and taking images and then recovering the payload. As I mentioned before, we have quite a bit of margin on the end. We have about an extra month and a half margin that we can dive into if we need to, but the goal is to have no other sort of outstanding tasks as far as the needing to change any of the design by middle of June, so that at that point we will just need to do the flight payload build. With that, I just want to thank everyone again who has taken the time to listen to this. Um, Hopefully you guys can give us some great feedback just like you did last time. If you can send that feedback or that feedback form that Professor Gamba will be sending out to either Professor Gamba or to Owen, it will provide us a great opportunity to continue to grow and develop this payload. And with that, I hope you guys enjoy your morning, evening, afternoon, whatever it might be. And thank you guys so much. At this point, we are going to allow some questions from Professor Gamba, and we'll answer those as best we can.